Hi everyone. So I'm, I guess, the science. Is that bad, David?
Science and passion for a material, I
Passion
think.
for this particular coastal exposure we call. So I think a few of you came to the last Water and Stone, so I guess go back and watch that talk online, but I'm going to skip over a few key points from that one just at the start so we're all on the same page. And we're going to dive into the bit of coast between Rinsey to Megiliggar, and we call this in the granite, we call it the roof zone, so this talk I called In the Granite Attic or In the Pluton Attic. I'm going to talk exactly about what that is in a second. But just a quick reminder, Cornish geology, I'm sure lots of you are well aware, but I just make sure we're all on the same page. Here we are, a map of southwest England. We've got, I guess, couple of key points to pick out here. We're all about, I think, as you mentioned probably yesterday, Ruth, so I can make your talk about an ancient ocean and the closure of this ancient ocean and creation of a mountain range during a geological event we call the Rinsey and Megiliggar. And then the subsequent.
Actually, I didn't talk about
Oh,
this.
you didn't? Okay. The kind of subsequent collapse of that mountain chain and the extension of our tectonic plates again. So in southwest England, we've got the remnants of this ancient mountain building event. So we have what lots of people call the killers. So this is the stuff, and here in yellow and brown, these are the ancient, basically the ancient sediments that are at the bottom of the ancient ocean, and that we've kind of metamorphosed and squashed into our slates and things like that. So lots of people call this the killers, and these are up to around 400 million years old. And then in red, we've got our granites. And these came into the whole tectonic setting as we started pulling our plates apart at the end of the Rinsey and Megiliggar, and they intruded around 295 to 270 million years ago. So we had a really long period of time where we were generating granites in the crust. And I'm not going to talk too much about it today, but we do also have the lizard. I can't neglect that, right? I'm standing in Helston. And this is a bit of ancient sea floor that during this mountain building event we've kind of managed to shove onto the top of the crust and preserve to this day. And this is an ophiolite and it's well studied as well. But today I'm going to focus in on the granites. So just a quick reminder. Did you do this yesterday, Ruth? What is a granite?
Do it again.
Yeah.
I'll sit in there.
So I'm going to go with the technicals. So granite, from the Latin granum meaning grain. It's a crystalline igneous rock, and I know Ruth was speaking a lot about crystalline structures and things yesterday. The scientific term for a granite, it must have quartz, and it must have two types of feldspar, an alkali feldspar and a plagioclase feldspar. And there's just lots of technical ways that geologists work with this definition. But then we have other minerals as well, and in Cornwall what makes our granites really special is that we have our micas. So we have biotite micas, we have muscovite micas. These are the things, if you go to Porthcurno, they kind of stick to you. They're like the glitters, stick to you. And we have those, and we also have lots of tourmaline, so the black kind of needles you see. And I'll talk a bit more about Megiliggar in a minute, because we have green tourmalines, for example. This is our general definition of a granite. But granites are not one rock type, they're all the same. They are hugely diverse. Refer to last Water and Stone talk on that one. I think it's on the internet. And in Cornwall we can differentiate broadly 5 types of granite, and this is a map of all of the different granite types that we see in Cornwall and Devon. The 5 main types, we can broadly split them into 2 groups. We have an older group, so these are around 285 to 295 million years or so old. So in the light blue, so we've got the Elzasili, the Carmenelis granite, which David knows well. We have our Bodmin granites. And we also have a few little stocks that like Hemerdon, Kithill, Cligger, places like this. And these are all, they've got 2 types of mica, the biotite and the muscovite. And we term the 2 mica and muscovite granites imaginative, I know. Then we have a little bit of a break. And then we have a second set of granites. Our biotite and our tourmaline granites that we find in the monster that is Dartmoor granite, St Austell and Land's End. And these come a bit later. They've got a slightly different chemistry, they've got a slightly different character, and they are generally younger than 280 million years old. And lots of people think of Cornish granite with the really big feldspars, that you find those in these granite types. And then we've got our weirdos, as David alluded to, are kind of outliers. We're not 100% sure how old they are because we can't properly get a geological age on them, but we see them dotted. There's one just north of Dartmoor, the Meldon Alpine. We've got a few around St Austell, and then we have the Tregonning Granite on this bit of the coast. And these are what we call our G5 or topaz granites. And these are the ones that I'm going to talk a bit more about in a second. They're very special, and they're like one of my favourite rock types I think in the whole world, because they're just so weird. And we can have lots of debate in the geological space about when they formed, how they formed. We don't really know, and we're all still debating, which is part of the fun of science. But just to put all of these in, just put a picture of all of these different granite types up. This is an example of the diversity of the granites we have in Cornwall. So just to go all along the top, and then links to the classifications on the previous page, you can see that there's diversity in texture, in colour. Some of them have got these really huge alkali feldspars. Some of them have no big alkali feldspars. Some of them have these rounded quartzes, globular quartz type. Others have got like slightly different colours. So top right is actually Godolphin, but they're all quite different. I know I've been a bad geologist and not put a scale on all of those, but you can kind of get a sense of the diversity of the textures that we see and the colours that we see in South West England. And then we come to these ones, our topaz granites. So these have quite a different texture actually to a lot of the other granites that we find in South West England. I describe them as being quite sugary in texture. They're actually quite fine-grained relative to other granites that we have. In geology terms, we call that equigranular, because lots of the minerals are a similar size within the rocks. They're pretty rare, but you can find those alkali feldspar phenocrysts. You have to look really hard to find them though. And then what makes these different to all of the other granites in South West England is that they have a lot of topaz in them. So topaz, you can't actually see it in this picture because it looks like the quartz. It's only when you get these rocks under the microscope that you can really start picking out the topaz. They also have quite unique micas. So in lots of the other rocks, they have dark micas. In these rocks, the micas are golden or silver. They contain an awful lot of lithium. And so we have lithium group micas in here. They're called zimmeldites and lepidolites. But this is something that's quite unique to this granite type. And from a scientific perspective, they're really interesting to kind of break apart, look out under the microscope, to crush up, to analyse their chemistry, because they've got a really unusual chemistry. Lots of lithium, lots of fluorine, loads of niobium, tantalum, tin and tungsten. They're very different to the rest of the granites that we see in South West England. And we also see them associated with these topaz aplites. So an aplite is a very fine-grained type of granite, and pegmatites are a very coarse-grained type of granite, particularly on the coastal exposure at Megiliggar, and I'll show you some pictures of that in a second. So just kind of to put some labels on that last picture, I'm not sure you can pick out too well, but just seeing the different minerals within this piece of topaz granite, which comes from Rinsey Cove. Just to add, all of these were taken with permission to sample. There's challenges with accessing some of these locations on the coast. And then if we take a look at what that looks like under the microscope, this is when you start to pick out the topaz. So I always think these look like just beautiful art pictures. I quite like to have them on the wall in my house. But you can pick out topaz. It's really distinctive. It looks like someone's drawn a line around it in a dark pen. This is something that's distinctive about topaz under the microscope. And we also have lots of tourmaline. So these are like a yellowy coloured grains that you can see in this microscope slide. And this kind of banding that you see in the tourmaline is called zoning. It's sort of like a geological tree ring. It's as the chemistry is changing across this crystal, as it's crystallising in a melt, that is what is being recorded in the colour change. And as a geologist, you can get out a laser. It sounds very dramatic, it's not that dramatic, but you can get a laser and you can kind of draw across this mineral and measure the different chemistry, and you can pick that up through kind of in the lab as well. But that's what it looks like in one light under a microscope. And then we put, I guess, the equivalent of a pair of polarised sunglasses on a microscope, and it changes the colours to give us different optical properties. And this is the same image with those kind of microscope sunglasses on. I don't know if that's the best way to describe that brief. I don't see you nodding. But yeah, polarised light. But it's just to pick up the different colours and things and the optical properties. They're very different compared to some of our other granites that we have. So if we zoom in a bit more into Tregonning Granite, which is getting into the Granite Attic now. On the left is a map from the 1970s. So this part of the batholith, all of the granites as a collective, has been recognised as being what's termed the roof zone for quite some time. I think one of the first references maybe in the 20s. But there's a guy called Maurice Stone, who people might know, might have heard of, I'm not sure. He did a lot of work on Cornish geology, 60s, 70s, 80s. I think he maybe into the 90s actually as well. And he produced a really good map, an initial map of what the Godolphin and the Tregonning granites look like. You can see this here. And you can see at the top there, he describes this as being the Tregonning granite and roof complex. And what you can also see is that Godolphin granite is mapped differently to the Tregonning granite. And so the Tregonning granite is our G5 topaz granite. The Godolphin granite is probably older. We don't really know. It's quite hard to get a date on the Tregonning granite. But it's it's got a very different chemistry. It's much more like a very fine-grained version of the Carmenellis granite, the stuff that David works with in the quarry. And we think it's older. So we've got two granites, different ages, probably different processes how they've come to be in the crust, sitting next to each other in the same space. This map has been refined over the years. This is kind of one of the latest ones. Came from, this was actually from my PhD a few years ago, where we think actually the Tregonning granite mass is bigger than perhaps originally mapped. And we can also see these green lines are the different mineral loads that are cross-cutting it. So we've got our granites. We can't also forget about our mineralisation, which often is granite derived in southwest England, also cross-cutting this space as well. So that's what we look like if we're looking down. And then Maurice Stone did one of these kind of cross-sections. Did you share this yesterday, Ruth?
No, this is all, I kind of kept away from all
Oh,
this
no,
stuff.
it's all right. I'm just checking.
Yeah.
Sorry for sort of like
That is one of my
repeating.
favourite all-time
Yeah, so I agree. Ruth just said this is one of her favourite all-time cross-sections, and also agree. I also like the ones at Megiliggar on the north coast. We've just got our cross-section through the Tregonning Godolphin granite on the coastal exposure here, and you can see that he's kind of just called it what you can see the granite in the kind of, I don't know what you call this pattern, this kind of pattern with lines on. Then we've got the mylar beds, or archillus, in the black, and then we've got this white section which he calls the roof complex, and this is like the really exciting bit that geologists around the world love. So when a granite comes into the crust, we don't always see, or it's not always preserved, what happens when that, because the granite doesn't just come into being, it has to come into another rock because it's an igneous rock. It comes into our crust as a magma and it crystallises and it cools. In Cornwall, those granites have come into the chylus. And so here we've got a really great exposure as to what happens when that granite meets that chylus. And at the very top of the granite, it's like full of water and lithium and all these different fluxes and weird elements that don't like to sit in our quartz. They don't like to go into the feldspar. And so they create this kind of really dynamic, complex cap, if you like, on top of the granite where it meets the chylus. And that is what we have exposed along the southern bit of the coast here. And yeah, it's quite, we don't always have it exposed, so it's great to have like huge coastal sections where we can kind of look down through the chylus into the roof zone, the top of the granite, and then down into the granite as well itself. And that's why lots of geologists love to come and explore this bit of coast, because often you can't see it, something like this, in such great detail. How long have I got? Check me time. Good.
You're doing fine.
Good. So much could be said. So I've just checked on a couple of Google Maps images, because actually you can go home and do this yourself. So this is Rinsey. It's obviously got lots of sand when this satellite image was taken. I recommend going to Rinsey when there's not a lot of sand. It's better for the geology. But if we look here, you might be able to pick out some kind of creamy bits. This bit here. You can see a bit over here, and then there's like a darker bit here, and I can't reach because I'm too small, but like here. And you can see there's a line going up there. So what you're looking at in a plan view here is the contact between the dark chylus and the pale granite. And geologists, we like to go out and map stuff, so we can make a map. So if I flip between that one and that one, it's kind of a map. And what you see when you go down to Rinsey is the kind of where we're sitting in the top of this roof zone where the granite meets the chylus. And in the middle of the beach, if the sand's not there, you've got lots of the mylar slates. You can find a nice granite vein on this side of the beach. It's pretty cool. And then we've got the Tregonning granite. And this is a really good space to explore what happens when that granite comes into contact with the Killis. I'm just going to show you a couple of pictures of this bit of the beach over here. If you there's like a sort of platform, isn't there, at Rinsey, you can kind of climb up onto. And in the Killis here, there's some quite cool textures. So as the granite has come in, it's kind of baked the Killis, and the Killis has got kind of what's happening? Reacted to this heat, this subtle pressure from the granite coming in, and it's recrystallised into lots of like little needles. And again, I've been a very bad geologist, not put a scale on, but these are small and these are bigger. Terrible, isn't it? Awful. You'll have some in a minute with my feet in size 4, just for reference. But so this is what happens. So the granite's come in, it's kind of baked the Killis, it's turned it black. This is baking. We've cooked the Killis. And some of the minerals within the Killis have effectively had a little freak out, and they've moved around and they've recrystallised as andalusite in all of these little needles. You see there's kind of no structure to them, they're just kind of all over the place. And in some places they're much fatter. They've got a lot of iron in them. They've sucked up a lot of iron, which is why they're kind of orange. So there's one thing we can kind of, geologists as they're looking around and going, well, what happened when the granites arrived in Cornwall? This is a really good location to kind of work out. This is one of the things that happened. We can map how our Killis has reacted as that granite has come in, and we can start thinking about maybe this tells us about the temperature of the granites, it tells us about the potential pressure of the granites as they were kind of coming in. A metamorphic reaction frozen in time that you can go and have a look at on that platform at Rinsey. And we can also start at Rinsey looking at what the granite looks like and what happens in the granite when it comes into contact with the Killis. So we've got that relationship with I'm looking at what's happening in the Killis. So now what about the granite? And we've got lots of different things that we can see. So in the top left, where the little hand lens is, you can see it's dark. This is the Killis. And then underneath we've got the granite. And the granite has done something crazy. It's got kind of trapped in under the Killis, all this fluid, all this like water, all this lithium, all this phosphorus, lots of different things. And it's crystallised on quite big white rectangles, I hope you can see. And these are alkali feldspar phenocryst. This is a pegmatite. And you can also see a zone of black, that's loads of tourmaline, because there's lots of boron effectively trapped in this kind of cap underneath the Killis. And you can see again in the top right, more of those kind of, these kind of splays of alkali feldspar. We call this texture a Stockscheider, in German. Obviously described at first in the Erzgebirge in Germany, which is another Variscan area, but in Germany, on the border with the Czech Republic. And this is again near the top of the granite. Oh, sorry. Thank you. Got a pointer. Wow, amazing. Yeah, so these here. So this is again where we've got the granites kind of come into that cap, into the top, met the Killis, and all of these fluids and things are kind of trapped, and it's crystallised these. And there's often a misconception in geology that big crystals like this, they take millions of years to form. Actually, this has happened in a relatively short geological period of time. We think maybe thousands of years, not very long at all, because there's so much influx in this space at the top of the granite in this roof zone, that all these fluids and things, all this water and things kicking around, and changes in pressure and all these different things happening, it's caused the really fast what we call nucleation and growth of these crystals. So they've actually grown in a very quick time. Can't quite put time on it, but much quicker than perhaps we think. You can also look at other relationships. So this is the granite vein referenced on the map, and this has got a sharp contact. It's coming quite quickly. It's cooled probably quite quickly, but there's almost no alteration. You don't see the andalusite here, and the granite looks pretty uniform. So we've got different ways that the granite is kind of interacting with the Killis. And then finally, it's a bit of a weird view, this one. There's a kind of cave as you come down the steps, kind of slightly onto the beach, and then to your left. If you look up, there's a big mineral lode, and it's got a huge granite sheet running through that cave as well, and where it splits and it kind of makes kind of crazy patterns on the ceiling of that cave. And so this is the granite here, another bit of granite here, it comes back together, it's kind of all over the place, and then it's cross-cut by a mineral lode. So we can get the kind of relationship. We've had the Killis, then the granite comes in, and then at some point later we've got our mineral lode cross-cutting. So we can start to create a geological story just by going and looking in a single cave. If we go to Megiliggar, Megiliggar, it's my favourite place. My favourite place in the whole Baffliff. I love it so much. Access very challenging. Definitely don't sample here. There used to be some steps you could climb down. Last time I went, just before COVID, they're gone. So if we're looking again down in using Google Earth, you can probably pick out like areas of dark, again, Killis, light, granite, but it's really patchy at this point. So dark, light, dark, light. It's very, very, very tricky. The map looks a lot more complicated. And we've also got an elven, which is a kind of granite rock that comes after our granites that are written about a lot in Cornwall, up in Legareth Zorn being the Cornish word for inlet, and a big mineral lode as well towards the kind of eastern end of the coastal section. But here we've got something incredibly complex, and this is like a really exciting bit of the roof zone, and this is the bit that granite geologists love. And what we have are these sheets, which we call the Megiliggar Sheet Complex, the MSC, just because we have to put acronyms on everything. And it's in these sheets that we can start to understand a lot about granite processes, and a lot of understanding of granite processes and pegmatites and aplites actually have come from people studying this coastal exposure. It's globally, geologically significant, but it's quite hard to study them because they're very high. So we can look at them in the fallen blocks on the beach, and they have the most incredible textures. We call this line rock in geological terms. It's just, but what we have is here we go, this is where pointer's going to come in handy. We've got pegmatite, the coarse grained granite with the big crystals. We've got zones of granite that's kind of medium grained, as we call it. We've got these fine grained zones of aplite. We have these dark bands, which might be rich in tourmaline, they might be rich in mica. We've got sulfide minerals in different places. We've got, and all of this is all cross-cutting each other. So this is another example. You might be able to pick out a structure coming down like this. So this is where we've got a few layers, and then you think a bit like a molten plastic that's kind of cooling. We're going to shoot another bit of molten plastic in there, and it's going to like shear everything and move things around. This is kind of what's happening. So we've got so we've got all the different layers. Another one's come in. We've started maybe like crystallizing another layer up here. It's all incredibly complex, and by studying the kind of section through these rocks, this doesn't all happen like from bottom to top either. It's always like one bit comes in, then another bit's there, then another bit might be below that, and it's all a real mix of something crystallizing, something molten coming in, the fluids building up, and just this incredibly like dynamic, like crazy, absolutely weird, to be honest, kind of granite setting in the roof just below the Killis, where we've kind of trapped all of our fluids. I've got one more picture. Okay. It was almost too sunny this day to take photos actually. And what we can also tell at Megiliggar is as we go along the beach, those big sheets get thinner and thinner and thinner. And there's always been a kind of argument of, okay, so what happens? And they just go away. You can't actually tell. So this is like a lot of the debate as we get back towards where the steps are or were. You can see the sheets are still here. This is a guy called Axel Muller for scale. He's quite tall. They get thinner and thinner, and they start to kind of move around. And we've got one coming down here like this, but they kind of just peter out. And there's always been a lot of debate whenever I've been down there with other geology groups as to why this is. Like what happened? Like what happens? We don't really know. But again, we can figure out some of our relationships because we've got our Killis in the dark, cross-cut by our granites. All of it is cross-cut by mineralisation. So we can again kind of create that story. And Megiliggar Rocks has also been a really great place for geologists to understand what happens when a granite meets a metamorphic rock or something like our Killis. And you can see some just incredible examples of these types of contacts. So I'm actually going to start in the bottom left. So this is part of the line, piece of like line, very top of a line rock where it meets the Killis. And this is the Killis, and it's effectively peeling the Killis apart. So this is like a moment where we've started peeling apart our slates as that granite has come in, and it's just kind of frozen in time. And I just love it because you have all these, this is a bit of Killis here that's kind of been peeled apart. So it's just a really crazy texture. And when you look at that in thin section, there's just a very odd mineralogy. You kind of get tourmalines and things just crystallising just on the edge of the chylus. But yeah, so really complex. We also have relationships like this. So again, it's quite handy because the colours are quite, creamy, orange, granite, dark chylus. These are what we call kind of bridging veins. And because our chylus is kind of slaty and you can kind of peel it apart in layers, the granite exploits this and it kind of cuts through those layers as it's come in. And then every now and again, it might meet some kind of barrier and it goes, oh no, I'm going to go this way. And it kind of joins up with the rest of the granite again. So it's kind of coming in and I don't know if that's a very helpful noise, but do you know what I mean? That's in my head, that's what the granite is doing, like millions of years ago. It's kind of coming into the chylus and kind of finding its way through the weaknesses in the chylus and kind of finding itself. It might kind of split and then come back together again, and it does that all the way along that section. And this in the top left is kind of a slightly more dramatic version, and the one in the top right, that is probably about 2 meters nearly, that what you're viewing in that picture. And it's just where we've kind of we've started with a bridge and we've kind of broken off a bit of chylus and it's kind of become frozen in time in the rock that's come in. And again, just bottom right is just kind of showing again the relationship between the granite and the chylus as it's kind of come in. And we can do lots of mapping to try and kind of understand the mechanics of how a granite gets into the crust. We can kind of understand it from here. Right, I think I'm nearly done, promise. Oh yeah, there we go, look. But yeah, so I guess just to emphasise, I've not dug too much into science. I have a website, there's a page about this Megiliggar and also a page about Rinsey on there. But just to kind of emphasise just how special it is as a place, how unique it is to have all of this preserved, and how important this location has been for our kind of global understanding of the mechanics between a granite coming into the crust and then how it interacts with the other rocks that are already around it. And equally, we still don't really understand quite how we formed this very weird granite, and that is applicable globally, I would say. Still the debate's ongoing. But yes. Thank you. There we go. There's the website.
I think there's a little bit of time for a few questions. Yeah,
Or
5
comments and
minutes.
thoughts, yeah. Just give me go on, Anthony.
Sorry, can we just go back to the other slide, the last slide a minute?
This one?
Yeah. Like, how instantaneous is that moment? Like, is it thousands of years? Is it an hour? Is it, I don't know, it's like, seems really amazing to think about how a molten granite was moving another piece of stone.
Yeah, I think a bit of a question mark. It's not that long, but in geological terms, it will still be thousands of years, I would say. I don't know if other geologists in the room want to comment. I think the thing also that's important about these rocks, these granites, is they're really actually quite low temperature compared to other granites, but they have crystallised incredibly quickly. So whereas over thousands of years, rather than like a couple of million years. So this would have been, in geological terms, quite quick, but in our own timescales, still quite slow. So that's a very non-answer. But I think what we're also seeing is we're seeing a process in action, which I find really fascinating. So this peeling apart of this chylus might have happened quite quickly. It's this bit here where we're starting to kind of effectively like assimilate the chylus into the granite, which you can't necessarily see very well in this photo, but you can see it when you look at it in thin section. We're starting to kind of really like alter the minerals that are in the chylus and get them into the granite effectively, and I've got better pictures of that, and that would have taken longer. So there's kind of a range of timescales of different processes in this one photo or in this one. I'm not sure if that helps answer your question.
Yeah, no.
Question mark. We can't resolve this in the lab in terms of time. Like we can't, there's no method currently, unless something's moved on massively in like the last few years, but we can't resolve geological time because in this kind of section, because we can't, the errors on when we do our analysis all overlap, so we've got no idea what the truth is in terms of time.
What about temperature? Because I don't understand. That's something I really don't understand. Is that you've got something very fixed there in photographs, so we're looking at this, and we're looking at something that you're saying could potentially take thousands and thousands of years. But presumably the Earth is constantly changing, the environment and heat, cold, wet, and all the rest of it. How is that impacting that little thread that looks like something that's grown in it?
Yeah.
Was that fixed? Was that fixed during the time when all these things were cooling or warming, or what was it? What's the temperature in the centre of a mass of granite, for example? You know, what's the relationship to heat and cold in stone?
Yes, oh gosh, that's a really big question. I'm not going to really answer this very well. I'm going to go back to this map because your question about temperature is quite interesting. So granites form at different temperatures. So when the temperature of the magma as it comes in, we can make estimations on what that temperature was. It's very hard, I think, to answer the question of how that evolves over millions of years. But from the kind of estimates of that initial starting temperature, the red ones, hotter generally, 800 degrees-ish, 850. The blue ones, a bit cooler, 750. The green ones, quite unusual because they've got lots of water, they've got lots of lithium things in them, probably about 680, which is, an interesting, I'll open a can of worms of just getting too technical. So when this comes in, it will have come in at probably about 680 degrees, but then will have taken thousands of years to crystallise and cool. But it doesn't crystallise in one go. It will be like a quartz or a mica first or a feldspar first. So you'll always have little pockets of melt. It's like putting loads of ice cubes in a bowl. Like they'll melt slowly over time. We're kind of doing the opposite. So you'll always have different pockets of melt that are kind of left in there that are still very, very hot versus these kind of crystals that are crystallising from the melt. So it's quite complex then to map the kind of temperature through time. I don't know if that's probably really not a very good answer, but I think probably the most important thing about all of the questions around temperature are these are highly unusual kind of more low temperature granites, and they still manage to kind of peel apart the chilus and start effectively melting the chilus into themselves. Which is really cool.
Is that low temperature because of the pressure in there? Because they're quite low temperatures relative to the universe, isn't it?
Yeah, so granites are, say if we go to Iceland, where we're making new crust, that type of igneous rock is very hot, whereas granites, as a crustal rock, they have lots of water, they have lots of lithium, other elements in there that lower the temperature of the melt. So granites generally are around kind of 750 to 850 degrees. These ones lower again because there's so much weird stuff in them. It just kind of lowers their temperature even further.
So if we put a bit of granite in a kiln.
People always ask me this, can I melt it in the kiln? No, sorry. No. So when we melt them in the lab, we have to take them, crush them into like a powder, so it's like a flour, and then we mix them with what is called a flux, which helps them melt at a low temperature, about 1,000 degrees. So they have to be kind of mixed together to make a glass. Because it's, as I was just kind of saying, it's not as kind of like, it's not just the granite melt comes in and it all crystallises into one. It'll crystallise through time, different minerals at different times. And so when we melt it, again, different minerals will melt at different rates, etc. So it's all very complicated, but we do melt them. I think you put something in a kiln once, actually.
I was going to.
Yeah.
We're probably going to have to stop
Yeah,
questions
no,
now
that's
as
fine.
well.
Yeah.
And there will be time at the end to
I'm
ask
afraid.
more questions of all the wonderful speakers. But yeah, I've lobbed a few blocks of granite in kilns, and it kind of, some of it stays together and some of it kind of degrades, but it doesn't generally go. It kind of holds itself together. There's some good descriptions there. There's always a good description. Yeah, I find. I'd just like to say thank you very much, Beth. That's amazing.